This conference will now be recorded.
Hello everyone. So last day we have already covered heat capacity and specific heat capacity. Now based on this topic, heat capacity and specific heat capacity, we will solve this problem and also we'll discuss today what is molar heat capacity. Under molar heat capacity there are two terms, Cp and Cv. We'll also see what is the difference between Cp and Cv. That is the relationship between Cp and Cv and also related problems. Here we have the problem which is based on, that is heat capacity we have to use. It is molar heat capacity, as you can see here. Fine. So 2.2 gram of nitrous oxide gas is cooled at constant pressure of 1 atmosphere from 310 Kelvin to 270 Kelvin. So this is the problem. Okay, before that, before discussing this problem, I'd like to finish molar heat capacity because there are total 3 topics related to heat capacity. So first we have seen what is heat capacity, and that is denoted by capital C, which is only heat capacity, and there is no term involving mass. Then we have seen small c, which is specific heat capacity. And now the third point is molar heat capacity. Okay, so 3 heat capacities: heat capacity, specific heat capacity, and molar heat capacity. So molar heat capacity, now we are starting. Based on this, once all this finish, then we'll discuss problems. So molar heat capacity, that is denoted by Cm. So this is heat capacity, specific heat capacity, and now the third one is molar heat capacity. So molar heat capacity Cm, that is defined as the amount of heat required to raise 1 mole of a substance, to raise, that is temperature of 1 mole of a substance by 1 degree centigrade or 1 Kelvin. So what is the difference with specific heat capacities? In case of specific heat capacity, it is per unit mass, and when it is only heat capacity, there is no mention of mass. So that is the difference between these 3. In heat capacity, there is no mass term involved. In specific heat capacity, there is mass involved, but it is mentioned as per unit mass. It may be per gram or it may be per kg. But when we are talking about molar heat capacity, now it is per mole. So the quantity is fixed. It is 1 mole. Rest of the things are same. That is, again, we are considering for increase in temperature 1 degree centigrade or 1 Kelvin, what should be the requirement of heat. That is the definition. Now, relationship between this heat capacity and molar heat capacity is this one. So molar heat capacity is basically heat capacity, that is capital C, divided by number of moles. So Cm divided equal to capital C divided by number of moles. N is number of moles. So in this case, molar heat capacity, the unit is joule per Kelvin per mole. Try to remember the unit for heat capacity. It is simply joule per Kelvin, or it may be per degree centigrade. When it is specific heat capacity, the unit is joule per Kelvin per gram or per kg. But when it is molar heat capacity, now the unit is joule per Kelvin per mole. So when you look at the unit, then also you will be able to understand which value is given. Is it Cm, is it capital C, or is it small c? So molar heat capacity, it is very similar to specific heat capacity. But remember, in specific heat capacity, it is per gram. But now we are considering per mole instead of per gram of the substance. Now it is also intensive, just like specific heat capacity, because specific heat capacity it is already mentioned for per gram, but in this case you are also mentioning a particular fixed amount, which is per mole. So it doesn't vary with the amount of substance, and doesn't vary with the amount of substance means what? It is intensive, it is not extensive. Fine. Now molar heat capacities, it may be 2 types, that is under 2 different conditions. One condition is under constant volume condition. Now you will call it as Cv, capital C subscript V, and if it is constant pressure, you will be using the term Cp. Now the subscript is P. So molar heat capacity, that is at constant volume. We know at constant volume, if you consider the corresponding amount of heat, that is actually QV. QV means subscript is V. So QV is the amount of heat involved, that is denoted by QV when the condition is constant volume. And we also know that QV is equal to change in internal energy. Okay, so change in internal energy, that is now, as we know that from the definition, amount of heat required to raise 1 mole of a substance by 1 degree centigrade and 1 Kelvin. So you can now consider that QV is equal to Cv into del T, and QV is also equal to del U. So if you know the value of Cv and also del T, you can calculate what is del U. And similarly, when it is constant pressure, now the amount of heat involved is Q, subscript is P, because pressure is constant. Now QP will be now equal to molar heat capacity at constant pressure multiplied by temperature difference. But QP is also equal to enthalpy change. So del H is also equal to Cp into del T. So now we are getting two relationships. These two are basically for 1 mole. So that is why mole N is not mentioned. But if you are considering the general expression, suppose there are n number of moles, any number of moles, n value may be any number. So now the relationship, that is del U is equal to ncv dt and del H is equal to ncp dt. These two relationships are very important. When we will solve problem, we will use these two expressions. That is a relationship between change in internal energy, change in enthalpy with Cp and Cv. Okay. So these two terms now we have learned. Now based on these two terms, we have to know the relationship between these two, Cp and Cv. So we will prove that. What is the relationship? We know that H is equal to Q plus P. Fine. Now when it is 1 mole from ideal gas equation, sorry, it is capital T, we know it is PV equal to nRT, but N is 1 mole, so PV is equal to RT. So in this equation, we will put in place of PV, now we will put RT, because PV is equal to RT. Now both side, if you take del sign, okay, now del RT means what? This is actually, this term if you expand, it will be T del R plus R del T. But del R is 0 because it is constant. There is no del R possible. So this value is 0. So only we are left with R del T. So finally we are getting del H minus del U equal to R del T. Suppose this is equation 1. But we already we have seen that del H is equal to Cv del T and del U is equal to Cv del T for 1 mole of gas. That is already mentioned here. So put these two in equation 1 and finally you are getting, cancelling del T from both sides, you are reaching this final expression Cp subtract Cv, that is equal to a constant value, universal gas constant. So this is the relationship between Cp and Cv, and from this relationship it is also clear that Cp value is greater than Cv because this quantity is positive. So it means Cp value is obviously greater than Cv, right? So from this mathematical expression, we can now conclude that Cv is greater than Cv. But if you want to know theoretically why Cp is always greater than Cv, then we have some explanation also. So what is the explanation we can give for this question? Suppose when it is constant volume, then heat transfer to the system will change the internal energy only as, because del V is equal to 0, right? So this part is completely, that is, there is no contribution from P del V. So no contribution from P del V because this quantity is already 0 because it is constant volume. But when it is constant pressure, Now the heat transfer to the system, that will be used up for two purposes. One will be increasing the internal energy, and also it will do some work, because now volume is constant. So P del V term, now it is not zero. So whatever heat we are, that is whatever heat amount is involved, it is actually doing two work. That I mean to say, it is actually doing two things simultaneously. One part is increasing the internal energy, that is del U. Another part is doing some PV work, mechanical work. Because now P del V is not zero, it is not constant volume. Fine. So that is why under constant pressure condition, there is the value is always high. That is the heat transfer that is always high. So this is the reason Cp is always greater than Cv. And the relationship is Cp minus Cv is equal to R. Now we will solve the problem that we have here. So 2.2 gram of nitrous oxide gas is cooled at constant pressure of 1 atmosphere. So here pressure is 1 atmosphere. Now as it is cooled, that means temperature will decrease, and the value is 310 Kelvin initial, final is 270. Okay, causing the compression of the gas from 217 0.1 ml to the value 167.75 ml. Fine. So the change in internal energy of the process, del U, that value we have to find, and that is already given in the form minus x, where x nearest integer, that nearest integer we have to find. Some more informations are also there. What is the atomic mass of nitrogen and oxygen? 14 and 16. And molar heat capacity of this oxide, N2O, that is also given, 100 joule per Kelvin and per mole. So as it is molar heat capacity, just look at the unit. It is joule per Kelvin per mole. Even if it is not mentioned molar heat capacity, then also just looking at the unit, you will be able to understand that it is 100 joule per Kelvin per mole. And molar heat capacity, as it is already mentioned here, constant pressure. Look at the line carefully. It is already mentioned constant pressure. That means this value you can consider as if it is Cp. So we have to find del U. Now del U, from first law of thermodynamics, we know Q plus W. And I will put a subscript here, which is capital P. So first what we'll do, individually we will find out what is W and what is QP. Once you know the individual values, now you can write, you can get the value of del U. Now as it is QP we know, instead of writing QP, you can also write del H. So finally the expression is becoming del U is equal to del H plus W. Now del H, how it is related to Cp value? It is N Cp del T, right? Now here you need the value of number of moles, but that is not directly given, you have to find it. So to find that, you should know what is the molar mass of N2O, because atomic masses are given. So N2O, 2 nitrogen, that means 14 into 2 plus 16. So this is actually 44. So if it is 44, number of moles will be given mass 2.2 gram divided by molar mass, and that is actually equal to 1.20. So now put here 1 divided by 20 multiplied by Cp. Cp is this one. It is joule, it is not kilojoule, so it is okay. And then temperature we have to put from 310 Kelvin to 270. So we can write it here. Now if we do the calculation for del H, you will see, sorry, here final temperature is 270 because it is gas is cooled at constant pressure starting from 310 up to 270. So I will write it first. So it is basically 40. So minus 40, and here we have is 5. So it is basically minus 200 joule. So now we are done with del H. Next we will find out what is W. Now W is, here it is mentioned, it is compression. Okay. So work is done on the system. So W is equal to P external into del V. Now P external is given 1 atmosphere. Look at this. So we will put 1 atmosphere. Now it is compression. So starting from 217.1, we are compressing it up to the value 167.75. So here we will put, okay, we have to do some unit conversion. So directly we cannot write it like this. See, why I am saying unit conversion? Because this value is joule. So when you will put it in the equation number 1, which is del U is equal to del H plus W, del H we have already found in joule unit. So W should be also in joule unit. But if you are using these ml values, or for pressure if you are using ATM, then you will not get it in joule. So you have to change the unit, right? So when you will change the unit, now how it will be? So 1 atmosphere is basically equal to 101,325 Pascal. 1 atmosphere is equal to 101,325 PA. That means Pascal. W will be negative. Okay. Compression 1, it will be negative. So 101,325, that is the pressure. Now final volume is 167.7. So first write it in ml, but after all ml you have to change to meter cube. Now 1 ml, if you want to change to meter cube, it is basically 10 to the power minus 6. Okay. So after putting it here, simply write the value that is given here, minus 217.2. Now divide this whole quantity by 10 to the power 6. So 1 ml is equal to 10 to the power minus 6. So as I am dividing it, so it will be 10 to the power 6. Now there is already negative sign here, and as the final volume is lesser than the initial volume because it is compression one, right? So it will also be negative. Negative, negative will be cancelled, and ultimately you will be left with positive value, and that will be 5 joule. If you do the full calculation, you will see it is 5 joule. So ultimately we have already obtained the values of del H, the value of W, and finally we will write the equation 1. So del H we have calculated minus 200, and now it is plus 5. So be very careful about the units. Here it is okay because you don't have to change any unit. But in this case, this 1 atmosphere you have to convert to Pascal, and as the volume is given in the unit ml, you have to change it to meter cube. So you are doing this unit conversion, you have to multiply 10 to the power minus 6. Here I have written it in the denominator. So that is why I have written 10 to the power 6, not minus 6, right? And as it is compression work is done on the system, there is a negative sign. So this negative sign, and here the final volume is lesser than the initial volume. So these two negative signs will be cancelled. Finally, it is positive. Ultimately, when you will put it in equation 1, you will get this result. So this is the final answer, minus 195, but see here it is already given in the form of minus, so you just have to put the value of a, so it is integer type of problem, so the actual answer is 195 without the negative sign. Got it? Next problem will go 1 mole of an ideal gas, that means here n value is 1, expansion, reversible, adiabatic, from a temperature of 27 degrees centigrade. Now if we convert it to Kelvin, it's 300 Kelvin. So we know the number of moles, we know the initial temperature 27 degrees centigrade. Work done during the process given 3 kilojoule. Now in terms of joule, it will be 3000 joule. This is another information. You have to find the final temperature that we do not know. Okay, one more information is there. Cb value. That means at constant volume, what is the molar heat capacity? 20 joule. That is also mentioned. Now, if we use the equation, that is First Law of Thermodynamics. Now, adiabatic process, so it is 0 plus W. So finally, del U is equal to W. Now, instead of writing del U, here you will write N Cv dt. That means T2 minus T1, final temperature, initial temperature 2 and 1. You can also write TFTI, and W, that value is already given, 3000 joule. Very careful, it is kilojoule. Don't put 3. It will be 3000 because left hand side unit will be joule. Now NCV dt, N value is 1. So it is 1 into 20 joule. T2 value we do not know, but you know what is T1 because final temperature we do not know. So we will simply write T2, initial temperature, and there is 3000. Now as it is expansion, 3000, okay. T2 minus 300. T2. Finally, we'll find out the value of T2. CVDT sorry, there will be a negative sign. Okay, so negative sign, so minus 150 plus 300. So ultimately we are getting 150 Kelvin. So 150 Kelvin, that means here correct option should be option C. So final temperature is 150. That means here temperature is decreasing compared to the initial temperature because initial temperature is 300 Kelvin. So final temperature should be lesser than this. Okay, so that is why it is there is a cooling going on. Final temperature is less. So option C, that is the correct option. Next problem. A gas, its molar mass is given, which is 280 gram per mole, was burned in excess oxygen in constant volume calorimeter. Actually, in calorimeter, even if it is not mentioned constant volume, then also you have to consider it as constant volume. That is the criteria for calorimeter. Okay, and it is as it is burned in excess oxygen, that means it is basically combustion reaction. Temperature increase starting from 298.0 up to 298.45. So the increase is basically very less. If you take the difference, it is basically del T is equal to 0.45 Kelvin. If the heat capacity of calorimeter given 2.5 kilojoule per Kelvin, look at the unit, it is given in kilojoule because it is heat capacity of calorimeter, so it is a very high value. And enthalpy of combustion of the gas is given 9 kilojoule, again kilojoule per mole. So enthalpy of combustion, that means del H value is given 9 kilojoule per mole. Amount of gas burnt, that is mass basically, that we have to find. Okay, so what are the informations given? Molar mass given. So if you can find out the number of moles, as you know the molar mass, you can easily get out what is the total amount involved. Simply multiplying number of moles with molar mass. Fine. So here we have to find out basically the number of moles. And what are the informations given? Temperature difference we know. Heat capacity, that also we know. Moles number, enthalpy, that also we know. So these are the informations given. From these informations, first we'll find out number of moles. Once you know the number of moles, now we will multiply with it the molar mass, which is 280 gram per mole, that is already given. So suppose the mass involved is x gram, which we have to find out. So this number of moles, that is equal to x divided by 280. Now heat released by this number of moles, that is equal to heat capacity, which is 2.5 heat capacity joule per Kelvin. That means it is basically capital C into del T. So capital C is 2.5 and del T is 0.45 kilojoule. Both are in kilojoule, so that is why you can directly multiply it. Now if it is heat released by x divided by 280 number of moles, then heat released by only 1 mole, that should be simply 280, it will come to the right hand side. So now it is 2.5 multiplied by 0.45 into 280 and x will come in the denominator. Okay, so this is the heat released by 1 mole. Next step, what we will do, as it is mentioned constant volume calorimeter. Now one condition that we have to keep in mind, that when it is constant volume, the heat given off or absorbed by the reaction, that is also equal to the change in internal energy that occurs during the reaction. That means we know that individually constant volume, that is when it is QP, that is del H. When it is QV, that is actually del U. But there is one more thing, when it is constant volume condition mentioned, under that condition del H is also equal to del U. Why it is so? Because the relationship between H and del U is this one. Now constant volume means this part will be 0. So now these two are actually equal to each other. So del H is equal to del U. Here enthalpy of combustion of gas, that is mentioned as 9 kilojoule. That means this value is given as 9 kilojoule. But as according to this condition, you can also say that del U is also equal to 9 kilojoule. So here this relationship is true. Now as why we are talking about this? Because del H value is given 9 and this value is basically equal to del U. Because it is constant volume calorimeter, whatever combustion is going on, that is inside the calorimeter and that is under constant volume. So the heat released by 1 mole, this quantity that you are getting, or you can say that heat released by x by 280 mole, this value is actually equal to del U, because it is under constant volume process. So this quantity, though it is del U, but you can write as 9 is equal to this quantity. Only we can write it because del H is equal to del U. And now finally from this equation you can write that x is equal to 35 gram from this calculation from this equation. So 35 gram, which we have considered as that is a starting amount of the gas for which molar mass is 280. So this is the answer, 35 gram. Okay. So just to have this equation, we have to consider this condition where del H is equal to del U. This quantity is nothing but P del V basically. Whether you write P del V or del NGRT, whatever it is. But actually del NGRT, if you write, you will not be able to understand why del H is equal to del U at constant volume. But if you put P del V, now it is clear that at constant volume, this quantity is 0. So that is why we can say there is a special condition where del H is equal to del U. And we will, that is, utilize this fact to write this equation, because once you can write this equation, then only X value you can get. And here one more thing, that we have not done any unit change, because everything is given in terms of kilojoule. Heat capacity given in kilojoule, enthalpy is also in kilojoule. So left hand side 9 is also in kilojoule, right hand side also in kilojoule. So we don't need any unit conversion, that is from kilojoule to joule, that conversion you don't have to do. Now we have a neutralization reaction problem. Heat of neutralization, that is enthalpy of neutralization, that we have already seen in the last class. But why I'm discussing it right now, because this question is also involving specific heat of water, or you can say specific heat capacity. Sometimes it is also mentioned as specific heat, but it is actually specific heat capacity. You will be able to understand it from this unit, joule per Kelvin per mole, joule per Kelvin per gram. So this is basically specific heat capacity, where per unit mass is considered. It is not per mole, it is per gram. So specific heat capacity is involved. So that is why I'm discussing it now, because heat of neutralization, this part we have finished. So this problem is basically combining both the concept, enthalpy of neutralization, and also specific heat capacity. So what it is saying that 600 ml of 0.2 molar nitric acid, you are mixing it with 400 ml of 0.1 molar sodium hydroxide in a flux. And as it is exothermic reaction, we know reaction between acid base, it is exothermic reaction. So there is rise in temperature because heat is liberated, and that rise in temperature, that is del T value, is dash into 10 to the minus 2. So whatever quantity we have, that we have to find in terms of degree centigrade. Some more informations are also there. Enthalpy of neutralization, and this value, that is 57 kilojoule per mole. This is true for any strong acid and strong base. In terms of kilocalorie, try to remember the value I have mentioned. It is 13.7. In terms of kilojoule, it is 57, and this is true for any strong acid and base. One more information, specific heat capacity, and you have to neglect heat capacity of the flux, because in the flux the reaction is going on. So suppose the flux, if you do not neglect, that means the flux can also absorb some heat, and then this amount of liberated heat, that is this dash into 10 to the power minus 2. So some amount of heat is also absorbed in the flux. Then calculation will be different, but in this case it is simply mentioned, you can neglect that. Okay, so the increase in temperature for this enthalpy of neutralization, that is a 57 kilojoule per mole, that is actually the energy liberated per mole of water produced in this reaction. So that amount of heat, that is only utilized in the rise of temperature. It is not absorbed by flux. So that is why it is important to mention here this condition. Fine. So the reaction, first write HNO3 reacts with NaOH. It will produce a salt, which is NaNO3. So it is already balanced equation, right? 600 ml, molarity 0.2. Now, when the volume is given in ml and concentration is given in molarity, if you directly multiply these two, as I am doing here, you will get the amount in terms of millimoles. So it will be 120 millimole. Why it is so? Because see, molarity means what? This is the number of moles that is present in 1000 ml. So 1000 ml is containing 0.2. That means 600 ml will contain 0.2 divided by 1000 multiplied by 600. 0.2 divided by 1000 multiplied by 600. So if you omit this 1000, it is basically 600 multiplied by 0.2. This is actually in terms of mole, but if you remove 1000, it will be in millimole. So that I have written it directly here. So in terms of millimole, this is 120. Similar thing if you do for NaOH, 400 ml, 0.1 molar, you will get 40 millimole. So basically, initially you have started with 40 millimole of the base and 120 millimole of the HNO3, and these two quantities 0. Now what is the limiting reagent? NaOH is the limiting reagent, and you have taken some excess acid. So excess acid after reaction, it will be remaining in the flux. So we don't have to consider. So from 40 millimole, obviously 40 millimole of NaNO3 will be produced, and 40 millimole of water will also be produced. Now this is completely consumed, so I am writing 0, and here some excess quantity that will be left, but we don't need that. We are just interested in this value, 40 millimole. Now in terms of millimole, it is actually 4010 to the power minus 3. This is the number of moles of water produced. But why we are doing this? We are doing this because enthalpy of neutralization, that is given as 57 kilojoule per mole. And you now know what is the total number of moles involved. So heat liberated that is actually equal to 57 kilojoule per mole. We will convert it to joule. So 57 joule 10 to the power 3 multiply total number of moles involved, which is 40 into 10 to the minus 3. So these two will be cancelled. Now you are left with simply 5740. You don't have to do the calculation here, we'll do it finally. Suppose this is equation number 1. Next equation, another equation. We need the value of mass. Mass is equal to volume into density. Now as in the medium, here water, on the basis of water we are doing the calculation, and this is 600 ml, this is 400 ml. So whatever volume involved, even after reaction is complete, total volume will be 600 plus 400, because you have not added anything else. Total volume involved is 1000, and density you can consider as 1 because nothing is given here. So simply consider the density 1 because it is the density of water. So mass involved is 1000 gram. But why mass is required? Now we will see what is the reason. Because heat liberated, that is also equal to heat gained, because that heat is utilized in the rise in temperature of the flux. That means flux has taken this heat to increase its temperature, neglecting heat capacity of flux. So it is not, that is whatever heat is liberated in this neutralization reaction, that is completely taken by this flux and it is utilized completely in the increase in temperature. So heat gained, and that amount of heat gained is utilized in the increase in temperature, that is actually equal to M into heat capacity multiplied by delta. Now heat capacity it is given in that is heat, it is basically specific heat capacity per gram heat, that is mentioned 4.2 joule per Kelvin per gram. So per gram it is 4.2, but what is the total mass? It is 1000. So you will write 1000 4.2 in joule, and delta that we do not. Suppose this is equation 2. So equation 2 is equal to equation 1. So MC delta, that is equal to 57 into 40. So you can say heat gained is equal to heat liberated. So that is why finally we will write 1000 4.2 del T, that is equal to 57. So that is why I was saying that you don't have to do the calculation, you can do it directly here. So after doing it, you will see you are getting the value 0.452. Now see, look at the format, how you have to finally write the equation. It is dash into 10 power minus 2. That means it is 54.2 10 to the power minus 2. So nearest integer, if it is clearly mentioned that integer, then you have to take only the value 54. Okay. So del T is 54.2 10 to the minus 2 degrees centigrade, but we will have the answer as only 54. Okay. Next problem. Two flux, 1 and 2. This is 1, this is 2, left hand side, right hand side. So see, in the first flux, both are connected by a valve. Negligible volume. You don't have to consider the valve volume, you just have to consider volume of these two flux, left and right. They are connected. When the valve is open, the final pressure of the system that you have to find in bar unit. But look at the format, it is x into 10 to the power minus 2 bar. But you just need the value of x, integer answer. So in the left hand side, the amount of nitrogen given 2.8 gram nitrogen, temperature 300 Kelvin, and volume is 1 liter. Right hand side, it is again nitrogen, but amount is not the same, 0.2. Temperature, it is lower than the previous one, but volume is 2 liter, double. There are some more informations. Molar mass of nitrogen 28, R value we know it is already 8.3, but it is also given. 1 bar, that is bar to pressure, Pascal conversion, it is 1 bar is equal to 10 to the power 5 Pascal. So based on this, we have to find out the final pressure. Now before going to final pressure, first we will find out what is the final temperature once you have opened the valve, because initially these two flux are isolated, they are not connected to each other. Under that condition, these are the quantities or temperature that are mentioned. Volume mentioned, mass mentioned, temperature mentioned. But when you will open the valve, now what is the final temperature? First we will find that. As mass of nitrogen given, you can easily calculate the number of moles involved in flux 1 and in flux 2. And when you will open the valve, what will happen? This temperature will decrease and this temperature will increase. So ultimately there will be a temperature which is something in between 300 and 60. It will be intermediate, something intermediate. Okay. So we will use this condition that number of moles present in 1 and 2 initially, that is before opening the valve and after opening the valve. Obviously number of moles will not change, it will remain same both sides. So you can write it, this condition you can consider. And one more thing, assuming the system attains a final pressure of T, which is in between 300 and 60. So that is why it is written in this way. And heat lost by the first flux, that is also equal to heat gain by the second flux. Because in the left hand side the temperature is high, so when you will open it from high temperature, now there will be movement of gas in such a way the temperature will gradually decrease for the left hand side flux, but for the right hand side it will gradually increase because it is gaining heat, and the left hand side it is losing heat, right? Now heat lost, that is equal to number of moles in flux 1 multiplied by molar heat capacity, which is Cm, multiplied by initial temperature, and this is T. That is, as it is lesser, so we have written 300 first, then it is T. Okay, and because it is heat lost, So there is a negative sign you can consider, but if you are considering negative sign, then you can write T minus 300 because final temperature is T. So if you normally follow the convention that we do, that is we write the final temperature first and then we write the initial. So in that case, it will be T minus 300. But if you are doing so, you have to put a negative sign, heat loss, as it is heat lost. But as we are not putting the negative sign, directly it is written 300 minus T. And in the right hand side, it is heat gain. This is the number of moles in subscript 2 Cm value. And Cm value is actually same because same gas is involved. We have not taken more than one substance. It is only one nitrogen. One compound is involved. So final temperature T, initial temperature 6. So final is written first, then 60. But here we have written 300 first because negative sign if you consider, then 300 will come first. Now put the number of moles. Given mass is 2.8 divided by molar mass of nitrogen. 2.8 divided by 28. Cm cancelled because it is same. And right hand side number of moles given mass 0.2 divided by molar mass 28. So final calculation what we will get? We will get 284 as the final temperature. But that is not the final, it is not our answer. But stepwise if we do, we first need final temperature because ultimately we have to find pressure. But directly you cannot do so. First you have to find the final temperature. So this is the first step we have already done, final temperature. Next step that we have to do, suppose the final pressure is P and final number of moles, if you add these two together, what we have written 3 gram. It is basically 2.8 gram plus 0.2 gram. If you add it, it will be 3 gram. 2.8 left hand side, right hand side 0.2. So just add these two mass, it will be 3 gram. So that is why it is written total number of moles, add these two mass, then divided by 20. 3 by 20. Okay. And PV by RT. Remember the equation PV equal to nRT. That means N is equal to PV by RT. Right. So P we do not know, that we have to find. Volume is total volume. Remember total volume. One volume is given flux 1 liter. Another flux is 2 liter. So this is the total volume. Though we have to change the unit. But total volume is V1 bus plus V2. Universal gas constant 8.31 and temperature we have just calculated in the previous slide, right? Right hand side number of moles according to this equation 3 divided by 28. Now we will put all the values of V, R and T because only this quantity is unknown. All the other quantities you know. So put all the known quantities. And also you have to take care about the units. So P is equal to, just take R this side, V this side. So 3 by 28, this quantity is number of moles, N1 plus N2. Next, R value 8.31, unit is joule per mole per Kelvin, but here we have written it in this way. Then temperature 284 Kelvin. And volume is in the denominator. So this is basically the volume. Total volume is 3 liter. But as you are doing the calculation SI, because universal gas constant in joule, so 3 liter, which is nothing but decimeter cube. So for liter, you have to change it to meter cube. So that is why now it is 3 into 10 to the power minus 3 meter cube. After conversion to meter cube, this is the volume. So that is written here. And 10 to the power minus 5 bar per Pascal. Basically, you can also do it later, but here it is better you directly do. Whatever pressure you will get, you need it in form of bar, because look at the question. It is asking calculate the final pressure in bar x into 10 to the power minus 2. But if you are doing this calculation by using all this in SI, you are using volume, R value, everything is SI unit. So final answer you will get in terms of Pascal. But direct unit conversion is done here. So suppose you have obtained it as I'm saying A Pascal. But we know 1 bar is equal to 10 to the power 5 Pascal. So if 1 Pascal is unit, that is actually equal to 10 to the power minus 5 bar. So when you change the unit from Pascal to bar, you have to multiply with 10 to the power minus 5, and that is we have done. So that finally you can get the answer directly in bar. You can also do it later. Okay, but here it is directly done. If you suppose if you are omitting this part, you will get the answer as 84 to 87 Pascal. But ultimately, you whatever result you will get in Pascal unit from this equation, finally you have to multiply with 10 to the minus 5. That we have directly done. So that is why it is written here 10 to the minus 5. So the answer is this. But the format we have to maintain 10 to the power minus 2. So that is why the decimal we are shifting it to right hand side. Now it is 84.28. Nearest integer 84. So this is the format x into 10 to the power minus 2. We just need this quantity. So that is why the answer is 84. Okay. Next we will see Kirchhoff equation. So this equation full derivation we don't need. We will just try to remember what is the equation, that is Kirchhoff equation. There are basically two equations when we say Kirchhoff equation. And what is the significance of this equation? The significance is from this equation you will be able to know what is the influence of temperature over enthalpy change and internal energy change. That is the purpose of this equation. So the change in enthalpy and change in internal energy of any physical or chemical process, obviously it is not fixed with increase with temperature change. So that is why suppose you are doing a particular reaction at temperature T1 and you are doing the same reaction at another temperature T2. Now when it is temperature T1, there is a particular value of del H del U, and when you are doing at temperature T2, there is also a different del H del U. Now del H at temperature T1 and del H at temperature T2, these two del H, how it is changing when you have changed the temperature 1 to 2, that we can understand from Kirchhoff equation. So the change in enthalpy, internal energy of any process, chemical, physical, whatever, varies with temperature provided pressure is constant. If a system undergoes change from state 1 to state 2, then the equations will look like this. So see, del H2, del H1, that means enthalpy change at temperature T1, enthalpy change at temperature T2, the difference we have taken, that is equal to difference in Cp value, because Cp value will be, you will be having one Cp value at temperature T1, another Cp value at temperature T2. So the difference in Cp, that is mentioned as del Cp. And for internal energy, we are getting another equation. Here we are assuming heat capacities are not dependent on temperature. So what are all these? There is different quantities. Del H1, del H2, enthalpy change for the process at temperature T1, T2 respectively. So this is at T1, this is at T2. Similarly, del U1, del U2, they are the internal energy change for the process at the temperature T1, T2. So this is at temperature T1, this is at temperature T2 respectively. Del Cp is the difference in heat capacities of products and reactions at constant pressure. So difference in heat capacities of products and, sorry, here I have by mistake I have mentioned Cp value at temperature 1 and 2. No, this is not like this because it is already mentioned here. Heat capacities, we are considering that it is not dependent on temperature. Basically, heat capacities, it may depend on temperature, it may not depend. But when if you are neglecting it, suppose the change in temperature is very low, that is the difference between T2 T1 is low, under that condition you can consider it that heat capacities, they are not dependent on temperature. But don't think it is always true, it is not universal. Sometimes it may depend on temperature, but that is a special case. Special case means that the difference between T1 and T2, then it is high. But whatever we are discussing, it is in simple form. According to our syllabus, this is enough. Okay. So when temperature difference is low, T2, T1 low, under that condition, you can consider in that particular temperature range, heat capacity is constant. That means it is not dependent on temperature. So this difference that you are seeing, that is actually the difference in heat capacities of products and reactants. Suppose you are doing the reaction A plus B, C plus D. That means heat capacity for these two minus heat capacity of these two, that is actually del Cp. Del Cp, don't think it is difference in heat capacity for T1 and T2. It is not that. So here it is mentioned. Similarly, del Cp is also difference of heat capacities of products and reactions at constant volume. Okay, so these are the significance of all these four quantities. That is del H and del Cp, then del Cv, del U, and del T. So this is Kirchhoff equation, and based on Kirchhoff equation, if we solve this problem, it will be clear. So this question is saying that enthalpy of sublimation process for iodine. Sublimation process of iodine means iodine from solid state. Now it will be converted to gaseous state directly. So this is sublimation. Now here it is mentioned enthalpy of sublimation of iodine is 24 calorie per gram at 200 degrees centigrade. Specific heat of iodine solid, that means reactant, that is given 0.055, and for iodine vapor it is 0.031 calorie per gram per Kelvin respectively. Then enthalpy of sublimation of iodine at 250. So at 200, what is the enthalpy of sublimation? That you know, it is given 24, but you have to find it for the other temperature, which is 250 degrees centigrade. So we have to use Kirchhoff equation. So according to this equation, first we will see what is difference between dels, that is what is the value of del Cp. So del Cp is Cp of product minus Cp of reactant. So Cp of product 0.031 and Cp of reactant 0.055, and this is the value we are getting. It is minus because this one is lesser. Now we will put it in this equation because after all, remember there are two Kirchhoff equation. One is related to del U, another del H. We need this one because it is asking enthalpy of sublimation, not internal energy. That is not mentioned. So del H at T2, that we have to find, which we do not know. But what is del H at T1? That is 200, and that value we already know, it is 24. So if you bring this quantity in the right hand side, it will be positive 24, and these quantities, that is Cp into T2 minus T1, there will be negative because Cp is negative. T2 is 523 because you will change it to Kelvin. So 250 plus 273, it will be 523. Similarly, if you convert it to Kelvin, it will be this. So final calculation, what we are getting 22.8 calorie per gram. So everything that is Cp value is given in calorie, del H also calorie. So you don't have to change any unit, right? So we have not done any unit conversion. So correct answer is option 2. So we will end here. Thank you for listening.